What I want to do today is this document. This is an example that I'm going to do this in Excel because I want you to see the detail. I will talk about Lift, so this is a review for the midterm. After the midterm, we will do multiple linear regression using jump in great detail, and we'll be hitting algorithms one after the other. And we will be using material that we have done before the midterm. So, anyways, this example was limited, and I've enhanced it. And so I have these two files go together. This is Lift with jump. I'm really doing it in Excel, but I wanted the two files to have the same name. So that you know that they're related. And so there's nothing really new here. There are a few different interpretations of what a lift is. They are very similar, but I want to present to you a slightly different way to do the lift. So I made up 309 rows. So here you see, okay, I hope you can, if you can bring down those the things so we can have better, you guys can see better. This one, yeah. Okay. Is it? In fact, I can turn on the lights off if you guys want. Let me know. So, actually, the example in the jump documentation uses a bunch of cutoff points, and then at those cutoff points, they identify a few things that I will explain. So I've actually enhanced the example. So here you have 309 people. Okay, so 309 records right here. There you go. And everybody has been assigned a probability of being cancerous, right? So 1 means the person has cancer, 0 means the person does not. So these are actuals. And this is the probability that somebody will be cancerous, right? But these are actuals. So, so you can have a high probability, and in reality, you don't have to be cancerous. This is just a hospital has done that based on your family history, blah, blah, blah. Okay. And then what I did, these are cutoff points right here, and I will explain everything. It's all right. So here I will put in the cutoff point, 0.97, meaning if you, and you see how I highlighted it in yellow, anything above 0.97, anybody who has been assigned a probability of 0.97 or above will be predicted to be a 1. Okay? And you will see why I didn't put the values there, because now I also have a little bit of code that I wrote, okay, using the index. You're not responsible for, you will not be tested on this, right? So this tells me,
Professor?
yeah,
So would the 0.7 be the cutoff?
the 0.97.
To consider it being predicted being...
I just explained. What I said was this 0.97, okay, and I put in yellow the first line above, where the probability is above 0.97. If you are one of these people, you will be predicted to be cancerous. So all of this will be ones. Okay?
Okay.
This means that I look at the index. You see this 20? Is this 20 right here? And I will use the colors so you can make the relationship between the two. This says that you have 20 people whose probability is above 0.97. This is the number greater than the cutoff point. Okay? This 0.06 is 20 over 309. You see, I made 309, I gave it a name, total number of observations. So this number right here, this 0.06, click formulas and trace precedence, is 20 over 309. So it says 6% of the people have a probability greater than 0.97. Then, out of those 20 people, okay, out of those 20 people, how many are ones? So if you count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. This 16 here, okay, this 16 is the true positive. So if I look at this top 20 people, 16 of them are cancerous. 4 are not. You have 4 zeros. 1, 2, 3, 4. So, actually, this I have a 20 here. This 20 is the sum of the 16 and the 4. And this 20 represents the number of predicted ones. The example doesn't make clear what the terminology is, but I wanted to keep the same. Now, I calculate this number right here. So you see, this is how This is like the Excel thing. The 99, these are people who are for the whole, right, in the whole list. This number is the false negative. These are, in reality, actually ones. And the prediction is 0. So these are plus minuses. Okay. And what I did, if these three and this last one is the true negative. These are people who are zeros and they are predicted to be zeros. So anybody whose probability is below the 0.970 will be predicted to be 0 and negative. Okay. Now what I did here, I said that 190 is the total minus the sum of these three. So if you say 309 minus 16 plus 4 plus 99, it gives you that number. This is correct. Now, I can change. So you see these numbers, 20. This number right here is 100%. This is a probability. This means that 20 out of 20 are predicted to be ones. And the lift, now, the lift here will be calculated in a different way. So let me do a little bit of writing on the board. So what we have here is 309 observations. So total number of observations okay, of patients is 309. And the out of those out of those 309 let me see, wait a second. 89 are 83 actual ones. So the proportion of ones, of actuals, the overall proportion of ones is 83 divided by 309, and this is 0.27. Right? Now, I am going to look at a bunch of cutoffs. One of them is 0.97, and then you have 0.77, then it goes down to 0.33, 0.31, and there is one close to the end, I think it's 0.04. Yes. All right. So, here, and this is another definition, another way, popular way that they calculate the lift, and I'm going slowly because I want you to pay attention to my words, and you will see that it's basically the same thing as we did before, but for right now, I'm treating it as being different. The lift associated with each group. This is what I call a group when this is the cutoff point. So call this group 1. Group or portion, with each portion. That's what, each portion of the population of the sample is is the is the contribution that that makes so this is the what do they call it here? Fraction of ones in the portion over fraction of ones in the sample. So in the first portion, so this is portion 1. Okay? These are all the people whose proportion is above 0.97. So for portion 1, the lift is 1 over 0.27. Hope you're looking at the file. I'll go back and forth between the board. I know this is shiny, but we'll be going back and forth. See here, 20 out of, I should say predicted ones. 20 out of 20 are predicted to be positive. 1 divided by 0.27 gives you a lift of 3.7. This 0.89 is, can you see this a little bit? Maybe. I know the light, but I'll be going back and forth with the lights, and let me just make it bigger. Is it? When I make 0.77 my cutoff point, and I can go here, see 0.77, 0.77. Do you see the 36 plus 8? That's this 44, the total. And so the number of ones above the cutoff point is 39. 39 over 44. There's 44. This is the second cutoff point, and I calculate these numbers here as well. So, point 36 plus 40 plus 8 is 44. This is the total number above the point 77. And if you take let's see, it's 39. So if I go here and I count 1, oops. So if I go here and I say equals sum of, if I count all of these, oh, no, not here, I'm sorry, here. um, 35. Okay. I change the numbers. I don't have to, let's see, this is total. Regardless of what this number is, I created my own probabilities. So if I put 35 here, right, this number here, if I divide 0.89, see, I made up my own numbers, that's why. If I take this 0.89 and I divide it by 0.27, right, if I say equals this divided by that, then I get the 3.3. So, what I want you to get, and I think I have some small discrepancies with the numbers, but what I want you to get is this. Here, you look at the portion of ones, and that was 1 over 0.27. Then you look at this group right here. Okay, when my cutoff point is 0.77, then you look at the portion of ones here, and you divide that by 0.27. So you have the overall portion, the overall portion of ones, which is 0.27. And then for each subset, depending on the new cutoff point, you get the portion of ones here, and you divide that by 0.27. Yes.
So based off of this, is it a way of helping us choose like the correct cutoff value, or is it a
There
way
is no correct cutoff value.
So is it more like testing the telling us the accuracy of the model?
Okay. So what you do is this basically, right? usually people divide, they break it into, you can call each of these portions into a decile, even though it's not. So what you have is you take this group, then you take this group, and then you take this group, depending on your cutoff point. And you take the contribution of this to the item of interest, and you divide it by an overall proportion, which is 0.27. There are also other ways of doing it. But the idea in this example is you have different cutoff points. How do you decide the cutoff points? Any way you want. There's no formula for it. But then you, as you are choosing different cutoff points, and you can decide them to be in increments of 0.10, whatever, you want to eventually identify the best cutoff point. We did that before, and the best one is the one. Actually, let me ask you. How do you determine, we did that, what the best cutoff point is? Here is the ROC curve. Okay? This is the baseline. Here you have a square, 0, 0, 0, 1, 1, 1, and 1, 0. So you have the points A, B, C, and D. What is the best point here? Did that? Yes.
C,
No.
B.
B. Why? Because right here, see, this is FPR and this is TPR in the ROC. This is 1 minus the specificity, which is the same as 1 minus TNR. Why is B the best point? Yeah. Yeah.
And because it gives you the highest area under the curve.
That's correct. So, I mean, if ideally, if I wish I had colored, if the curve was covering exactly A, B, C, right? It would give you the biggest area under the curve. And what's the biggest area under the curve? The maximum possible value for AUC? Area under the curve. What's the maximum this can be? Yes. 1. If this curve goes A, B, B, C, right? Then you have the area of this, which is a square, and each of the sides is 1. So the maximum of this is 1. On this curve, which is the optimal point? Yes.
One is closest to B.
It is the point on the curve closest to B. What happens at this point? Go back to calculus a little bit. Yeah.
Oh, well, you, at that point, or I thought you meant point B?
At this point.
Well, you're minimizing, you're maximizing your TPR while minimizing. Your
That is correct. There's also, you can say something else from calculus, yes.
Isn't the slope zero?
No, the slope is at its maximum point. Both answers are correct. This point, the slope is zero if you pick this point right here. Let's say I pick this point F, the slope would be zero here. What is, and you can, if you go back to your calculus class, if you take this point here and that point here, you can approximate the slope. You have 2 points. Okay? This is x1, y1, which is FPR, TPR. This is x2, y2. Let's call this point GH. As G and H get closer together, right, this is called the secant line, if you remember. Right? And this is the tangent line. So, now this point is the optimal point because it picks the see, each of these points, if I take points G, E, H, to find points, G, E, H, we need a cutoff point and the FPR and TPR at that cutoff point. I have to remember to write big. So you actually have 3 dimensions here. FPR, TPR at a certain cutoff point. At another cutoff point, you'll have another point. Right? And you connect these points and you get the ROC. ROC works very well when you have a binary type of experiment, 0 or 1. If you have more than, and that's where I email your document to study, if you have more than 2 scenarios, like freshman, junior, sophomore, senior, whatever, then you do not look at that, okay? What is the meaning of this point right here? You see, each point on the ROC is a pair. This pair right here, the first number is FPR and the second number is TPR. So, this is the confusion matrix, confusion or classification. So this is your actual and this is the predicted. So here you have 1, 0, 1, 0, right? Now some people put 1, 0, some first, or other times they put 0 on. It depends on the thing that you're interested in. The thing that you're interested in, when I say thing, I'm talking about either a 1 or a 0, so, people put that first. So if 0 is the item of interest, you put 0, 1, 0, 1. I mean, you can put this any way you want. Okay. So this is the same as plus, is the same as positive. This is the same as negative, and like that, right? So remember that the horizontal total must be equal to 1, but not the vertical. So point B is the point 0, 1. That means FPR is 0 and TPR is 1. TPR is 1, FPR is 0. So this is 1, 0, and this is 0, 1. Okay? So, what is the meaning of point B? Yep,
It's accurate, there are no false positive or true negatives.
that's right. This says that all people who are cancerous, they take an X-ray, and they take a CAT scan, they go through an X-ray machine. The X-ray machine is the classifier. And that says that you're cancerous, so all cancerous people are identified as cancerous. And all healthy people are identified as healthy. That is why B is the best point. And what is the worst point? D. See, D is 1, 0. So 1 is, this is the FPR, and this is the TPR. Whoops. 1 and 0. Which means this is 1, this is 0. So this says that all cancerous people are, the X-ray machine, the classifier, tells them that they're healthy. And this says that all healthy people are told that they're cancerous. That is why. So B is the best point, and D is the worst point. Okay? All right. Any questions? I sent you a couple of hints. The way to, to prepare. I need to check some things with my numbers here, but you can take what I did here, and you can study after the course how I use the index, and to get these numbers. And actually, I should be looking here. That's why I said may delete. I should be looking here. I was looking at the complete, that is why. Okay, I was. So what they have here, okay, is you can take a look here to see how these numbers are calculated. These are given, all right. These are given, and say given or producible, and what I did was, okay, right now I don't want to go over the whole thing, but I generated the decile I took for each cutoff point, the baseline being 1 and the lift, and I plotted them here. So you see that the decile and the lift say the same thing. In the decile, this ones corresponds to this right here, this line. So if I was looking at this bar only, what does this tell me? Just this bar. We are reviewing. This tells you that if you pick this as the cutoff point, you will, the contribution to the ones is 3.7, what was that? 3.7 of the, is 3.7 times the overall contribution of ones, which is 0.27. And so this is a slightly different interpretation. Okay, slightly different. It ends up being the same, but on the x-axis you have the selected cutoff points. Okay. And I put some links here so you can use this file. Oh, they broke. All right. So, anyways. Okay. I just wanted to expose you to a different, slightly different interpretation of the lift, and this comes from an example that I took and modified that they have in the official JUMP 14.2 documentation. When they say low and high, high is 1, low is 0. So when they say number of high, this is number of ones. And I think when I made up my numbers, I messed up this a little bit. Okay. I have asked you to play these 2 videos. Did you guys do that? All right. I may play them for you in class. So let me talk about. I'm going to do some writing on the board. This is a recap of chapter 5. All right. So. All right. By the way, here you have some on homework quizzes, and there's a handout that I gave out. The quizzes, I leave them outside of my door, so you can pick them up from there. Okay, so we talked about measures of error, okay? And right after the midterm, we will start using them, right? And I talked about the mean average error, which is also another way, mean average deviation. Root mean square error, there's another name for it that JUMP uses, RASE. I forget what this stands for. And total sum of squared errors, okay? And there are formulas for this, okay? That I gave you. I want to make sure that I have that I put down all the formulas. So, mean average error. So, when we have a this is especially true in supply chain. We have actuals, okay, and predicted. instead of predicted, many times people use the word forecasted values, right? So they use A for actual and F for forecasted, or you use yi and yi hat. So error, right, is epsilon, or the ith error is epsilon I, which is the ith actual minus the ith forecasted, or if I do, or people use yi minus yi hat. These are actuals, these are forecasted. So this guy right here is, right, and so this is the Greek letter, but many times they use EI for error. You'll see all these notations. Let me stick with this one. So this is the absolute value over n. That's the one metric. The another metric is the average error, right? And this is that. Usually, I mean, ideally, I should say, okay? Ideally, this should be 0. Okay? The mapping mean absolute percentage error, mean absolute percentage error that's this mapping, right? This is actuals minus forecasted over actuals, the absolute value, and this is over n, and this is times 100%. So anywhere you see AI, you can put yi. Anywhere you see fi, you can put. So AI, yi, same thing. Fi, yi hat, same thing. So you can just replace. The root mean square error. This really says square root, okay? Square root of the mean or average squared error right? Squared error. This is actually, out of all of these, it's the one that people use the most. I would say this is probably the most useful one. And this is the square root, as it says, of the sum of the squared errors, the average of the sum of the squared errors. And this total sum of squared errors is simply this, right? For all of these, I is 1 to small n. Right? We will use these metrics once we start hitting one algorithm after the other. All right. I have limited amount of the board, so I'm going to erase those, but make sure you write them down. So other terms, things that you should know. Okay, cumulative lift chart. Or cumulative gains chart, same thing, right? This is when you have this. And you see how the cumulative, so this is contacted, and these are responses. So this is actual ones here, and these are the number of people contacted. This is the cumulative gains right? And this looks similar to the ROC. Yes.
It's not just responses though, right? It's like positive responses?
When
On the
I say
y-axis?
responses, we always mean positive responses. Yes, thank you. So this says here, if you remember, in the cumulative, right? So it's important to know your axis, right? So if this is, let's say, the 10%, I mean, this could be a number or percent. These are the top 10%. If you contact the top 10% randomly, right, you may have, well, we assume that the default is 10%. If you contact 10% and you use the model, let's say you contact your actual responses, your positive responses is 30%. So the lift, so the cumulative lift, the cumulative gains is 30%. But the actual lift is 30% divided by 10%. Right? The lift, not, when I say lift, I do not mean cumulative lift. If I want to talk about cumulative lift, I have to say cumulative lift. So this looks similar to ROC. Now,
Question?
yes,
So is that the cumulative lift or just the lift?
so the cumulative lift is 30%. The lift is 30% divided by 10% or 3. Okay? Now, if I look at this graph right here, okay, so these are conducted and these are positive responses. All right? I want to ask you, so here's the question. Use use this or some form of this to label the x-axis and the y-axis. Right? So I use TP, TPR to tell me this is the cumulative, right? So here we have the cumulative gains or lift cell. I want you to use this to label this and the x and the y axis. Take a couple of minutes. Okay? So when I say conducted here, right? And I have 10%, 20%, this is the top 10%. This is the top 20%. Okay? Top 30%. So these are sorted, these are subjects, right? They could be people, whatever, sorted by the probability of being in class 1 in decreasing order. Right? So if I was You see, if I use letters A, B, C, as you go up, right, as you go to the right, if this is A and this is B, I have the higher probabilities at the top. And this is actually one of the questions in homework 5. It was related to that. See, when I have a cutoff point, right? Remember, these are sorted from highest to lowest probabilities. So the probability, right, is 0.999, 0.998. Let's say this is 0.769, this is 0.771. Let's say the cutoff point is 0.770. Okay, so and here you have, you can have the actuals, right? And here you have the predicted. Now the actuals, can somebody, let's say I have six of them, 1, 2, 3, 4, 5, 6. Can somebody give me, so I have 6. So what should I want to put zeros and ones here. Can somebody give me a possible 6 values for this? Do you understand my question?
Yeah.
What is most likely?
One.
Most likely you'll have ones. But you may have a 0, right? So this is most likely, right? Most likely you'll have mostly ones. You should have mostly ones because you rate them by the highest probability of being in class 1. And down here at the end you should have what? Mostly zeros. But you may have an occasionally 1. Okay. Now, what should I have for the predicted values here? What should I have here? What should I have here? Yes?
All ones?
All ones. Why? Because we are saying anybody whose probability is above the cutoff point must be a 1. Right? And what should you have here? All zeros. Right?
Yep.
Okay. So these are the actuals, these are the predicted. If I take this and I move it sideways and I can put it right here. Now, so so you have the that's why I put the letter A and B. I have A at the top, B at the bottom. So this is analytics. This is at the heart, right? So if I was to to look at, let's say, the highest part, 10%, 20, 30, 40%, okay? And I was using a count. What would I use for the count? What letters? What on the x-axis, especially at the very top, look here, that's why I did this. Which one of these are up here?
True positive.
True positive and
False positive.
false positive. So here, this is if I was using, right, true positive plus false positive. As you're moving in the top, as you're moving to the right, right, you are going towards the other. Now, you can either, if you have a count here, you can have that, but you can also have a proportion, right, 10% like that. If I was using a proportion, then this is divided by the overall total. Overall total is the sum of all of this. This plus this plus this plus that. And here is the number of ones, right? Actuals who are also predicted to be actuals. The actual ones who are predicted to be ones. So this is the ones. So if you look at the top here, right? Here you have we have 1, 2, 3, 4, 5, 6. Out of those you have 1, 2, 3, 4, 5. So this is true positive over true positive plus false what? Negative. So these are ones, these are, hold on a second. This on the y-axis is true positive as a count, okay? And if I was to use a rate, I would use a true positive rate, which is what I had there. So, in other words, do you understand what I did here? In the beginning, right, on the x-axis, when we say conducted, these are sorted by the probability of being in class 1. Okay. So we talked about the ROC, the good and the bad points there. We talked about the cumulative lift or cumulative gain. We talked about the lift. Okay. And there are still other, later on in the course, we will see a definition of a lift which is similar to the one that I talked about today. That's why I don't want to spend too much time when we do market basket analysis. Remember that when you do analytics, you are playing with approximating something. Okay, so we talked about decile. When you have deciles, right, you want a good decile has to look like this. This is a good decile. It has to look like a staircase. If you have a decile that looks like this, so this could be 10%, top 10, top 20, top 30, top 40, and so forth, right? These are percents. The same thing here. Why is this second picture not a good decile? Yeah.
Because it's not sorted? Or
No, you have sorted and sorted, same thing, on the x-axis. Yeah,
Difference between the different bars is in 10.
I'm sorry?
Like the difference?
Same thing, 10%, 20%, 30%, 40%. So this is what one algorithm gives you, or this is you're doing your model in one company, you're doing your model in another company. Yeah,
Is it oversampling?
I'm sorry?
Is it oversampling?
No, I'm not sure where you
And
go.
it's not effective for you to choose the cutoff value because the cost is really high if you choose the 40%.
Say it again.
I was thinking maybe it's not very effective for you to determine which percentage to go for, because you can choose 20 or 40%. It has kind of the same value, but the cost is different.
You're close, you're going that direction, yes.
It's not showing that it's any better than doing random samples?
You are much closer. You see here, this, what you want, right? This says that if you pick your, let's say this is 2, this is 3. If you pick the top 10%, right, you will do twice as well as doing things randomly, but you're doing better if you pick the top 20%, which means picking at the top 10% doesn't really help you. You have to pick more people. The idea is to pick, the idea is to contact as few people as possible. This says if you contact the top 10%, then you'll have a lift of 4. Then as you're picking more and more people, right, this goes down as it should. But, so in other words, this is no good. You want these bars to go down because you want to pick more ones from the top 10% or 20%. You understand what I'm saying? All right? This here forces you to go to the 20% to the 40%. You want to avoid that. So a good decile is one that looks like this. All right?
Look, Professor,
Yeah.
how does the bottom one happen? How does that, like, how do you, what's different?
What's different is the bars. You see here?
But like, how does it happen? Like, how does it happen?
It can happen because even if you sort the people,